Hi, this is my video lab report for experiment 2, magnetic field of a bar magnet. I'll walk through the experiment, the physics behind it, my data analysis, my computational model, and the comparison between the two. The purpose of this lab was to measure how the magnetic field of a small bar magnet depends on the distance and use that to determine the magnet's magnetic dipole moment. Using a smartphone magnetometer, I measured the field strength at 5 different distances from the magnet. By plotting the natural log of the field against the natural log of the distance, the data should reveal a power law relationship, and theory predicts the field should fall off as an inverse cube of the distance along the magnet's axis. I'll show what I found, build a computational model of the dipole field and closed group, and compare that model's prediction to a real measurement taken at 45 degrees to the magnet's axis. 3 core ideas underlie this lab. First, a bar magnet behaves like a magnetic dipole, characterized by a magnetic moment mu, a vector pointing from the south pole to the north pole. Second, the general dipole field formula. B equals mu naught over 4 pi times 1 over r cubed times the quantity 3 times mu dot r hat times r hat minus mu. This expression gives the field at any point in space relative to the dipole. It simplifies nicely along the magnet's axis where mu and r hat parallel, and perpendicular to the axis where their dot product is 0. Third, the power law follow. If we expect the field magnitude to be following magnitude of b equals k times r to the n. Taking the natural log of both sides turns this into a straight line. Natural log of b equals natural log of k plus n times natural log of r. So a log-log plot lets us extract n as the slope. We also had to compensate for Earth's own magnetic field by orienting our setup so the bar magnet's field was orthogonal to it, letting us isolate just the magnet's contribution using the x component of the magnetometer. Here's how I set up the experiment. I placed the phone flat and rotated until the x component of the magnetic field read close to 0. This aligned the phone with the magnetic north-south. I then aligned a meter stick along the bottom edge of the phone so it now pointed exactly east-west. I oriented the bar magnets along this east-west axis, ensuring the magnet's on-axis field would be orthogonal to the Earth's field. Finally, I located the magnetometer chip inside my phone using the maximum-minimum technique described in the instructions. Here's what I observed. Far from the magnet, the measured x component of the field was near 0. As I moved the magnetometer closer to the magnet, the measured bx increased, confirming the field gets stronger closer to the source as expected. Here are my measured data. 5 distances R20 through R220 each labeled by the approximate field strength in microtesla I was targeting. Plotting natural log of bx against natural log of r, the spreadsheet's trend line gives a slope of negative 0.665 with an intercept corresponding to k of about 11.7. The theoretical prediction for the on-axis field is n equals negative 3, meaning the field should fall off much more steeply with distance than what I measured. My measured slope is notably shallower than what the theory predicts. This most likely explanation is incomplete compensation for the Earth's magnetic field, especially at larger distances where the bar magnet's own field becomes small and comparable in size to any small residual Earth field contamination in my x component reading. Small alignment errors that are negligible up close become significant far away, which would flatten the apparent slope. To extract the magnetic moment, I used the on-axis dipole formula. The magnitude of b equals mu naught over 4 pi times 2 mu over r cubed. Solving for mu equals b times r cubed divided by 2 times mu naught over 4 pi. Using my closest, most reliable measurement, R20, where r equals 0.254 meters and b equals 20 microtesla, I calculated a magnetic moment of approximately 1.648 meters squared. When I checked this against my other data points, the per point estimates vary quite a bit, from about 0.002 up to 1.68 meters squared, which again reflects a non-ideal power law we measured. I chose to trust the closest distance measurement most since it's least affected by any residual Earth field error. For the coding portion, I run a function called dipole b, which takes a magnetic moment vector and an observation location relative to the dipole and returns a magnetic field vector using the general dipole formula. I use this function to visualize the field at 7 locations, 2 along the magnet's axis, 4 perpendicular to it, and 1 along the line tilted 45 degrees to the axis, matching the real measurement I need to compare against. As expected, the field arrow points along the axis direction at the on-axis locations and in the opposite direction of mu at the perpendicular locations, consistent with the dipole formula structure. Now for the key comparison, how well does my computational model match a real measurement at 45 degrees? From my off-axis spreadsheet section at a perpendicular distance of 0.158 meters, the sensor ended up a total distance of about 0.224 meters from the magnet. After correcting for Earth's field, my average measured net field was approximately 8.39 times 10 to the negative 5th Tesla. Running my dipole B function at the same distance and 45-degree angle gives a predicted field this. Comparing the two, you get a 72.5% difference. 2 what-if questions. First, what if I hadn't compensated for magnetic north and instead laid out my meter stick at some intermediate angle? In that case, the bar magnet's field wouldn't be purely orthogonal to the Earth's field anymore. My measured BX would then be a mixture of the magnet's actual field and some leftover component of Earth's field, contaminating my isolation of the magnet's contribution. What if 2 identical magnets stuck together end to end instead of 1? Sticking 2 magnets north to south effectively doubles the magnetic moment. Mu total equals 2 mu. Since the field is proportional to mu, the on-axis field at any given distance would be roughly twice as strong. Several sources of error likely affected this experiment. The biggest was probably incomplete Earth field compensation, while other contributors include distance measurement precision, locating the magnetometer chip exact positions, and sensor noise. And here are the conclusions. I measured the on-axis field of a bar magnet at 5 distances, found a power law exponent of n approximately negative 0.665, shallower than expected, most likely due to incomplete Earth field compensation.